Well, I like to remind you the due date of each homework. You are supposed to upload your homework to Google Drive. You don't need to send me any email. You just upload it. Then I can always check the date, and then I can go through your homework. Okay, that's very important. And in doing your homework, you, especially the Excel programming, you need to do yourself, starting from a blank. That is very important. Well, it's not that difficult. Of course, you can start from other worksheet, such as the one I been developing in class, but in that way, you cannot learn yourself. You need to do it yourself from blank. I mean, each week you have to add yourself, okay? And go ahead, make mistake. That is a very important step in developing program. And then find the bug and go through all debugging process. That's the only way you can learn how to program. Okay, so also, when you submit the homework, you need to have some PowerPoint slide explaining, define the problem statement, and also some slide shows some result. I mean, so far you, most of you just upload the Excel file, but from this week, you need to have a PowerPoint together with the Excel and defining what the problem is, define problem statement and show result. Okay. Also, PowerPoint is very critical. I mean, way of explaining what you do. So Excel and PowerPoint is the one you need to submit. Okay, I'd like to just remind you that what we have done last week. Well, first, we start with on axis, okay, on axis stiffness. What is on axis? Well, on axis is the this axis along the fiber. This is X and this is Y. Well, there are many different definition of the index, especially coordinate, but this is the one we are using. So please stick to this definition. So X and Y is X again is along the fiber, Y is a transverse direction. Right now we don't have to pay attention to through the thickness direction, Z direction, since all the fiber rotation is with respect to a Z direction, so it's a XY plane. Anyhow, this is a XY coordinate, and this is the this indicates the strain, and this arrow indicates the stress. And now, what is a Q? Q is again Q sigma equal Q and strain epsilon, and sigma 3 component sigma XX. Well, you can just say sigma X, and this one sigma Y, and shear stress sigma S. That's the what we define, and also epsilon X and epsilon Y and epsilon S. Epsilon S is this guy. As a reaction, we have this guy. So we do have a 3 component of a strain and 3 component of stress. Now we have a 3 by 3 on axis stiffness. Okay, this is the on axis. On axis again is XY coordinate. And Q, how we get the Q? I just want to, we always start with the engineering constant, EX and EY and mu X and ES, right? They are from a material database in your Excel. And from this, we can have S matrix, right? Compliance, because one of the term, for example, SXX is the one of EX, and so on. So we do have a 3 by 3 S matrix, and Q is simply inverse of this S matrix. Okay, so Q is S inverse of this. So 3 by 3, and we have a 3 by 3 stiffness. Okay, very clear. Now the point here is that how do we get on-axis, off-axis stiffness? Okay, off-axis stiffness, or you can call it a reference axis. Reference axis means this is the off-axis, or you can call a reference axis. Say this one, with respect to, this is what? On-axis, and this is the reference axis or off-axis. So off-axis we using x1 and x2, and this is x, and this is the y. Now we do have a angle, theta. Theta is an arbitrary angle. So on-axis is the angle rotate from the reference or off-axis by theta. And also we have x and y and x1 and x2, and also this is a theta. Now the strain along the off-axis, we do have epsilon1 and epsilon2 and epsilon6. And off-axis stress, we have sigma 1, sigma 2, and sigma 6. Well, very similar to on-axis. Now, off-axis stiffness, now we are defining using the symbol Q bar. Okay, Q bar now relating the stiffness, the strain and stress. So point here is how do we get this Q bar so that we can easily relate this off-axis strain and off-axis stresses. So Q bar is nothing new, which actually can be calculated from on-axis stiffness with the angle theta, right? Now we are given theta, so we are having Q and theta. Now we like to calculate the Q bar. Okay, that's the flow, and you may wonder why do we need this Q bar? Well, Q bar will play the most important role in stacking and contributing to overall stiffness, because later we may have a zero or whatever angle, and we will stack them and put them together, and we will get the overall stiffness of this laminate. Laminate means the all the layered. This one you can call one ply. Okay, this is just one ply, and if we have many plies, then it is called laminate. Okay, so anyhow, this is what we went through last week, and we had all the Excel file. So this is the so Q bar is to can be obtained from these steps, because now we do need some mathematics transformations, and this one from here to there, we like to go through this and that step to reach here. In other words, we like to calculate, how do we calculate the Q bar? Well, Q bar is a same step as the strain. This is the strain, epsilon bar, and epsilon. Epsilon is the strain in on axis, and epsilon bar is the off axis. What is the relations? Well, relation is given as the strain transformations. Okay, strain transformations, you know, the Mohr circle thingy. And on-axis stiffness is the relating these relations. And once we have a sigma, how do we get the sigma bar? Well, there is another stress transformations. So here, pay attention, please. This is the Q epsilon bar here, because we are from epsilon bar to epsilon, and here is from sigma to epsilon sigma bar. So this T and this T, I will just call plus and minus. So plus means that we rotating in positive direction, because you know, here to rotate to this direction, and here from here and rotate to this direction. So this is the minus direction. This is a positive direction. So I add minus and plus. So while you may not remember all these transformation metrics, you don't need to remember. You can always refer to you know, this formula and that formula. But conceptually, you need to understand these procedures. Okay, this procedure, I think the most important steps in understanding how do we get off-axis stiffness from on-axis stiffness as a function of theta. So we went through this step 1, 2, 3, which means that you know, here sigma bar instead of the here sigma bar T sigma and sigma bar T sigma. Now sigma is on axis, so on axis is the Q epsilon. Now what is the epsilon? As you can hear, epsilon is the T and epsilon bar. So we put here, then finally we get these relations. Now by definition, this is what? This is nothing but off-axis stiffness. So conclusion is a sigma bar is the, I'm sorry, Q bar is from here to, this is the a function of what? Theta, and Q is the function S inverse, and S is the EX, EY, and mu X and ES. Okay, so we went through all these procedures, and here are the final results. Again, you don't need to remember, but one thing you need to pay attention to here is that, you know, the T is a second order transformation, and this T is another second order. What I mean by second order is the strain and stresses are second order tensor. That's why in transformation, we always have twice of either cosine or sine. Always twice, and twice, right? Either cosine and sine, and that is the result of the second order transformation. Now here, this is a second order, and here is the another second order. Now finally, it's a fourth order stiffness, fourth order. So actually the Q is the stiffness is a fourth order tensor.
So zeroth order tensor is a scalar, vector is a first order, second order the strain and stress, and there are third order tensor, which is very rare in physical sense, but fourth order is a compliance and stiffness is a fourth order. Okay, so again, these are only 4 components because this is the on axis, and here is all 0. 0. Why are they 0? Well, 0 means that we have on axis and there is a no normal stress and normal shear strain, no coupling terms. This is the coupling term. For example, epsilon x and epsilon y and epsilon s. And here is the sigma x and sigma y and sigma s, and equal q epsilon. So epsilon s times it here. So we don't have any coupling term. In other words, when we apply this, there is a no shear term, right? And vice versa. So here is always a 0. So anyhow, we do have only 4 terms and 4 terms, and we now in over axis we only we also have these terms. They are non-zeros. Okay, they are non-zeros. Here we have a non-zero terms. And as you can see that Q is the fourth order, so always 4 times of either cosine and sine. Here, always 4 times, right? 4 times of a cosine or a sine. All terms is the fourth orders. Okay, so this is the what we have studied. And we can complete this programming. Last week, we had only 1 terms, but we can complete that. I'll delete this guy. Okay, so here Q22 is as you can see here, Q22 is sine fourth order. Here, n is a sine, right? N is a sine, and cosine 4 times. I mean, a fourth order, and QYY. And so on and so on. Now we complete these terms 1, 2, and also Q 6, 6, and Q 1, 6, and Q 2, 6. So 1, 2 is what? This one, and we can change here and times and sine to okay, and just copy and paste. That's Q12, and here sine 4 plus cos 4. And here, instead of plus, we have a minus. Okay, right? So this is the terms. And Q 6, 6.
How about the Q66? I will just copy these terms and then see what's the difference. Difference is these terms. So I will just copy this guy to here. And here, -2. And here, oh, we are doing Q44. Okay. Plus minus and square and second order. Okay, so this is the Q66. Please check Q66, cosine sine, cosine sine, and minus cosine sine, and plus and sine cosine. Okay, that's good. And Q16, 16. Just copy and paste. And here, wait, cosine is m, right? M is a cosine. Wait, it doesn't matter. Okay, now Q16, cosine, m is 3, and sine is 1, minus cosine 1 and sine 3, and then this one just a plus m cosine sine 3 and minus cos 3 sine. Is okay? And then twice cos and sine and cosine 3 and sine. Okay. Okay.
Q66에서
Right?
마지막 QS 거기 앞에 사인하고 사인 반대로.
Yeah, it's a scale. It's the same thing.
그 앞에 사인 가로 안에 있는 사인하고 QSS 지금 교수님 그 체크하신데 바로 앞에 가로 안에 사인 제곱하고. 네,
코사인 제곱 빼기 사인 제곱.
Yeah, it's a scale. It's the same thing. Okay, you want to change it? Well, if you want, I can change it. See, same value. Now here, Q16, and we just change it. This is the 1, and this is the 3. And minus, this is the 3, and this is the 1. Okay, and 3 here, and 1, and this is the 1, and this is the 3, and also this one is the 3, and 1, and 1, and 3. Okay, good. Now again, you just copy and let me see. Now you just copy and paste up to here. As you can see that all these equations are same, but as you can see, all the value, all the symbols coming from these upper rows, so that each column you have different values according to same columns. I mean, I'm sure you already know that. One thing, now we get rid of this and get rid of this. Here, this one, it shows that just Q11 and Q22, okay, that's a vertical axis, and along angle, right? Along angle. So for that purpose, we just change this angle, okay, just for the purpose of showing the value, the variation of a value along the angle. And we also can do, now we like to select them all and angle here, and then plot. Okay, it's the same thing, but I like to just delete these two guys to magnify. Okay, so well, this graph show us how this all axis stiffness vary along the angle. But it's not easy to predict the value, but we do need to understand how each value vary. For example, Q12. Please take a look at the Q12. What is the Q12? That is kind of Poisson's effect, right? Q12 is the Poisson's effect. And as you can see that it varies from a very small, this is a stiffness, by the way, it's not the compliance, but you can see this value changing like that. And also Q66, very important term, Q66. What is a Q66? Shear stiffness, okay? Shear stiffness. Now, as I asked in last homework, Q66 is the reach the maximum value at angle it reaches angle at 45, right? It reaches the maximum at the 45, as you can see. And also Q16 and Q26. Well, Q16 and Q26, this one, it reaches at maximum at about the 30 degree, and Q6 reaches at about the 60 degree, and starting from 0. At 90 degree, goes to a 0 again. Why? What is a Q16 and Q26? That is the shear and normal coupling term. So whenever we have a
I mean, Q16 will be 0 in all on axis, right? Q16 is the 0 at 0 degree. 0 degree is the on axis. So it has to reach 0 and 0 here again. Now, the most important term is the Q66, for example. So we can further okay, this is the slide explaining why Q16 it can be non-zero for a certain angle. For example, if we apply a Q sigma 1, okay, this is the what? Normal stresses. This is the normal stresses. Q16 is the normal stress. And normal stress would cause the normal strain and transverse normal strain, but also a shear strain. So say sigma 1, sigma 2, and sigma 6, Q11, Q12, Q16, Q26, Q66, and Q22, and epsilon 1 to 6, okay? So these terms, Q16 is the one relating these terms and these two terms and these terms. Okay, so when we apply sigma 1, we have a epsilon 1 and epsilon 2 and also epsilon 6. Okay, epsilon 6, what is epsilon 6? It's a shear strain. So which you don't notice in isotropic material. Isotropic material, whenever you apply load, deformation is always like that and shrink. There's no angle change, right? No angle change. But in anisotropic, it can happen when you apply the normal. There could be also a shear strain changing. Okay, that is very important behavior. So Q16 will reach at 0. Q16 will be a 0 at theta equal 0. Well, which is nothing but Q16 will be a Q. 0. And another one important behavior will be well, a shear stiffness. Shear stiffness is again like that, and we apply a shear stress sigma x and relate to shear strain epsilon s. I'm sorry, we need to call sigma 6 and epsilon 6. Okay, so sigma 6 and epsilon 6, there is the term relating is the Q66. Now, why Q66 reach maximum at theta equal 45? Well, this one, say theta equal 45, okay, this is very important observations. At theta equal 45, pure shear is the same as, this is the same angle as above, and same as the tension and compressions.
this is exactly same. Why? If you remember the Mohr circle, this is the shear term corresponding to here, and 45 degree or twice over 45 is what? 90 degree. So here and there. I'm sure some of them, some of you forget many theory about the from the Mohr circle. Please go back to a Mohr circle and then need to study. So anyhow, here and there, say this term, this magnitude will be the same as the here, right? Since it's just a circle. So say this is the magnitude, say this is the sigma 0, just magnitude, and here sigma 1 will be the sigma 0. Here sigma 6 is the sigma 0, and here is a sigma 2 equal what? Minus sigma 0. So tension sigma 1, here will be sigma 0, here will be minus sigma 0 at 45. Okay, the point here is that this shear is exactly same as the tension and compression. This tension in 45 are supported by fiber. Very strongly supported by the fiber, and this one. So that's why the you get maximum at 45 degree. Okay, this is the answer you need to reach. So strain also epsilon 0 and minus epsilon 0. And that's why Q66 reaches maximum and 45. So whenever you want to design a structures, for example, a tube, which is supposed to this kind of a torque, okay? Say you like to design a cylinder or tube, which is supposed to support torsions. You know, torsion always what? Is shear always like that. So there will be a shear stress is like that. So this one better to have this way, 45 degree. Well, but one way 45 is not that strong. You need to have the other way 45 as well. So to make tube which is supporting torque strong is to have plus 45 minus 45. Okay, so 45 is the very typical angles to enhance or maximize shear stiffness. Okay, again 45 by the angle of 45. That's the way we support tension load by fiber. Okay. Okay. So this is the important observations, and I hope that you get the same result as here. Now there are some other slide regarding this off-axis stiffness using a identity relations between sine and cosine. Say cosine, this is nothing but cosine force order, force power, okay, is the same as the here. Similarly, you have say sine, which is the what? 1 minus cosine twice of theta, right? And cosine theta is what? 1 plus, right? And sine cosine is what? Sine, right? So very similar to this kind of identities, we do also have these terms. You can simply multiply of these twice, okay? Then you get these relations. Okay, of course you don't get this. I think it has to be second order. You don't need to remember this, but this is how you change from force power to just a double angle or 4 times of angles. Now, why this step? This step can be important. Okay, I will come up with results. So put all the relation into here. Okay, into here. So instead of that, you put that equation here. Instead of that, you put the equation there, and do all terms. And now here are the results. Okay, here are the results. Oh, look quite different. But here we defining new terms called U1, U2, 3, 4, and 5. Okay, U1, 2, 3, 4, 5. And U1 is in terms of on-axis property, 3/8 times QXX plus and so on. And Q1, U1, now Q1 bar, instead, you remember the Q1 bar is the M, QXX, and N, sorry, this is the, has to, right. And so on, right? Instead of that, we now have alternative relations. Okay, now instead, U1 is given in terms of here, and U2 is here, and 3 here, and 4 here, and 5 here. Okay, so this is the another way of relations, another way of this off-axis stiffness in terms of on-axis stiffness. Okay, well, let's do that. We just copy here and see here, what is this guy? U1, okay, U2, well, not much important, but you need to understand, instead of a U1, I used U underbar 1. The reason is that if you use the U1, U1 will be what, say, its own reference address, right? U1. So you should not use U1. Instead of that, I use the U underbar 1. Okay. So U underbar 1, 2, and 3, and 4, and 5. 3 and 4 and 5. Okay, so U1 from this table we can see, say 8 times QXX plus 3/8 times QYY, right, from this table, and plus 1/4 times QXY plus 1/2 times a QSS. Okay, so we use this one, and U2 is just delete this, and this will be 1/2, and here minus 1/2. Okay, and okay, let's copy these terms. And what is the difference? We just change this one and 1 and minus 1 and minus. And 4. Okay, this one 3 and minus. Okay. Right? Okay, so copy and paste. And then instead we minus here. Here is the minus, and here we have a plus. Okay. Now we don't need this, and we need to define these rows from these tables. We just click, and here, I'm sorry, all the menus are in Korean, but we cannot change to English. We're not allowed. Ridiculous. So anyhow, here, so that as you can see, here it's the U1 and so on. Okay. Now, next one is the this exactly same, okay, but different, a little different way of calculations. This guy now from this table equal what? U1, right? Plus cosine 2 theta. What is the cosine 2 theta? Well, we didn't define yet, right? So we like to define. We need to define cosine and cosine, sine. Okay, so let's say so instead of cosine, I would say cosine 2. Okay, let's use underbar. Here, sine 2. This is just a symbol, okay? We can define any variables. And here is the 4. And now cosine 2 is what? Twice of the angle. And sine, twice of the angle. And cosine, 4 times. And 4 times. Okay, so we are copying here to here, and then we define the name from this. Define name from left column. You say yes, and double check here that has the name cosine 2. Okay, so this is the how we define this double angle. Now here, let's type U1 plus, and cosine 2 theta, we use the cos 2 times U2.
Yes.
Okay, this table means is a times plus a cosine 4 times U3. Okay, so well, obviously this one is the same as this guy. Okay, let's complete these terms. Q1 to Q2 to U1 and difference is minus here. And copy this one. Q1 to this one is the U4 and no terms for this. And here is the minus. And now Q66 and U5 and minus, okay. Q16 and here we have what 1/2 times a sine 2 times U2, okay, plus sine 4 and U3. Okay? Yes. And copy and paste. And here, instead of plus, we have a minus. Okie dokie. So we just compute, just make sure that these values are same as this one. Oh, not the same. What's wrong? Instead of this, Q22, 1 cosine, 2, 3, up. Huh? Ah, really? Okay. Let me double check. This one, half. Okay. Oh, thank you. Thank you. So that's why I love Excel. We can easily find the bug. Now, double check this one and this. Okay, good. So we just copy and paste it here. And again, we just give a name from here. We don't, we already have a name, right? Okay. Now, we just can confirm that these values and these values are exactly same, right? Then why do we bother with this all second derivation, these variations? Well, this is the what I like to emphasize. U terms, okay, U1 to U5, what are they, what does, these terms means? If we plot them, very important observation, they do not change along the angle. All the U values remain the same, right? Very important observations. Of course, they are all function of material properties, right? So independent of angle. So they are called invariant. Now, the concept of invariant is important. So this one, we can get back to a definition of invariant, but say invariant, okay? Invariant, physically important concepts. Okay, so these are invariant, and I like to use this Q. So we changed the name. Oops. We didn't define the name yet, huh? Okay, so now this one has the older name, Q11, Q22, and so on. And we don't need to have this one. I just like to emphasize that all the off-axis stiffness can be in terms of this all invariant. Okay, invariant. What is the invariant? Well, I hope you remember the stress transformation. Stress transformation, for example, sigma 1 is the cosine sigma x plus a sine sigma y plus twice of the cosine theta and sine theta and sigma s, right? This is the stress transformations, but these terms, cosine theta, can be replaced 1 plus cosine twice of theta and sine and you know this way. So these terms, sorry, I'm gonna delete this one. This one, sigma x plus sigma y plus I forgot. Okay, this one, 1 plus cosine twice of theta, and this one, 1 minus cosine 2 theta, and this one is what? Sine 2 theta, okay? Let's put it here. So this half and half comes to here, and okay. And this is the minus, so, okay. So sigma x minus sigma y times a cosine theta plus sigma s times sine to s. Okay, so this one is like U1 and U2. So these are very similar concept to U1 and U2, and they are invariant. Invariant, so invariant in second order transformations, always a sigma x plus a sigma y. And this is the first invariant, and the second invariant is square plus sigma s square. Okay, this is the first invariant in second order transformation, and this is the another invariant. What does it mean? Well, if we go back to a Mohr circle, we always have this a circles. Again, this is the Mohr circle, right? And Mohr circle, whenever we have this is the terms, and we have this diameter, and then what? We rotate, right? This is, we are rotating by 2 theta. But which terms remain same? Always this center remain the same, and this radius remain the same. So what is this center? This center is this guy. Always this is the sigma, and this is the what? Sigma x and sigma s, And this term is a sigma y. Sigma y and sigma s. So this is a two coordinate. So this center is this one, and radius is the this one and that. What is this? This one is the sigma s, and this difference is this one. So this is the radius, and this is the center of the Mohr circle. So they remain the same. So physically they are invariant, which do not change along the angle. So this concept can be extended to a fourth order tensor. So U1, 2, 3, 4, 5, they are all invariant. They do not change. They remain the same regardless of angle. Now all the variation of this fourth order tensor are in terms of invariance. Very important physical concepts. Well, recently, Professor Steve Tsai, who I'm going to introduce more, proposed a new theory called trace theory using this invariant. Okay, as you can see here, this is not an old theory. This is very brand new theory called trace, a game-changing. As you can see, 2017, last year. So all theory is based on this invariant of the stiffness physically, and he liked to emphasize the using this trace or invariant. Calculating all the material properties. This is not much information. But anyhow, if we have a chance, we will get back to that one. The point here is that this Q, U, 1, 2, 3, 4, can be very important terms. Okay. Okay, it's a 2:05, but let's have a 10-minute break. Thank you. So we went through some derivations, and we the O-axis stiffness are all in terms of invariant UI, and UI again they are all invariant. And there is a 4 independent invariant. U1, 2, 3, 4, they are independent variables, but U5 is related to U1 minus U4 just because of relations. And those invariant concept is similar in stress and strain transformation. This is the, the I1, I2, and I3, all the stress invariants, and I1 is the center of radius of a Mohr circle, and this one is the radius. Okay, so now you can have all these terms, Q11 versus a ply angle for this material, and T300 and Scotch, and also aluminum, and find the ply angle which maximizes Q66. Well, you already went through this kind of a problem statement, so this is not our homework, okay? But I'd like to go through number 3, QIJ versus a ply angle for aluminum. You can expect that, say here, say aluminum. What is the EX? Well, about the 70 gigapascal, and 70 gigapascal. Poisson's ratio is about 0.3. And now important point is the shear modulus. What is that? One plus. We know this relation for isotropic material, right? Okay. Okay, so that is the third material. So from here, I'm gonna delete this. Oops. I'm gonna delete this. And this is the same. Oops. Okay. And this is not so important. Again, these are Q11, Q22, and other terms, variations. Now we select aluminum by selecting number 3, right? Number 3. So we just copy and imagine what will happen to this stiffness. Wait a minute. Something is not right. Okay, there's something it's not right. Okay, this one. Okay, I got it. 2, 3. I'm sorry, here I made a mistake. ES. Okay, this is the what? 2. And here is the 3 and 4. This one has to be 5, right? To refer to shear stiffness. Shear stiffness here, right? So I need to change this one, and then this. Oops. Okay, there are still something. Okay, this one, and then now why these values are not same? So these are the same as that. So we not here. Sine cosine. This not. This is okay. Okay. My determinant. Okay, I need to. So scale, we need to have a scale here. That was a mistake. You never be afraid of making any mistake. We always can find them. And okay, now they look weird, but don't worry. This is the just because of two small variations. So as you can see that they are all the stiffness remain the same in different angles, right? So if we change this angle like one is the T300, and so the behavior was very similar. So we didn't notice that, but we changed it to an isotropic material. Now we got this. We are able to find the bug. Okay, good, very good. Okay. Well, it is a usual steps. Whenever we program, we have to double check by changing the angle, by changing the material properties, in a way that this theory and programming can have bug free. Okay, that is a must step. Okay. Now where are we? We here, and finally, let's jump to stiffness of a composite laminate. That is the one of the core step in classical laminate theory. Driving laminate stiffness. Okay, using all the theories. Many over-axis stiffness in terms of angle. Okay, so here are the problem statements. Say we have a laminate. Now, what is the difference between the just stack of ply versus laminate? Well, laminate is the all plies glued together. Okay, glued together means that they have to deform together. They don't deform independently. They deform together. That is the laminate. Okay, they are all glued. Well, that is obvious, but here are they all glued. Glued. So deform together. That is the laminate. Okay, that is the laminate. Now each ply have the three information. First one is the what material is this? Okay, each one material is this. And what ply angles? Okay, what ply angles? And number of ply means that this guy, you can have a either thickness of a multiple of a unit ply, or you can have a number of plies. Which means that we have a same material, same angle, but we can have a many layers. In other words, same material, same angle, we can have a different thickness. Okay, it's the same story. So each, in this case, we can call a ply group or laminate group, a sub-laminate, but you can extend the concept of a ply. You just have a which ply, which material, and ply angle, and number of plies, or thickness. So each ply, you have a 3 information, like M and theta, and number of plies. Well, M, we don't use this one, but this is the one way of explaining each ply. And there is another symbol at the end, either T or S. T means a total laminate sequence, and S means that symmetric. So you show the sequence, just half of them, and the others will be same as the others, mirror images, okay? Mirror images. For example, this one, very standard layup. So always starting from the 0, 0, plus 45, minus 45. So this is the same as a 0, and plus 45, minus 45, and 90, and symmetric, okay, symmetric. This is the 90, and symmetric means the mirror symmetric. Mirror means that you repeat by mirroring these layups, 90, and minus 45, and plus 45, and 0 degree. So this is a symmetric, and this is the 0. You can say the 45 and minus 45 and 90 and 90, 45 minus 45 plus 45 and then 0. The reason in this case you need to enter T. T stands for total laminate sequence. The reason why we are using the S is that in practical application, we more than 90% all the laminates are symmetric. Okay, so symmetric is the very typical laminate. Okay, this is the a laminate sequence code. Well, instead of a comma, you can open and call just a slash. That's not so important. Now, the most important structural behavior of laminate is explained in this slide. Okay, we mentioned that laminate, in a laminate, all plies are glued together and deformed together. While this is a very obvious statement, but which will guide us to understand the behavior of a laminate and help us to formulate this behavior in equations. Okay, so since they are all glued together, okay, please, this is the most important one. Glued together, all the strain, this laminate, whatever we apply, bending moment or tension, shear, whatever load we apply, always the strain deformations, okay, deformations of each ply. Z means this Z. Z is each ply, are always given in terms of please pay attention to here. Z is a coordinate. Z means a linear. Okay, this is a constant term, and this is a constant term. It's like a linear function in terms of a Z. So uniform strain and slope. So this one, let's say we are extending. This is the extending, uniform extension. And another one is a bending. Bending is that this one is a curved like that. So if the top is the extended this much, and next one extended this much, and the bottom is a contract. So strain-wise, always this is the Z, this is the epsilon, for example, 1 is always Z equals 0. We have a certain value, and we have some strain like that. Again, this is a Z coordinate. And Z equals 0. What is these terms? This is epsilon 1, 0. And this is the A slope, which means that this is the A curvature, curved one. In higher order theory, you may think that, oh, there will be another term, Z square, another constant, plus the third power, and so on. But it is quite enough to consider uniform and linear terms. That is the conventional definition of a structural behavior, regardless of the material laminate material properties. Even in steel, okay, steel plate under bending or whatever load, always the uniform and bending. Even for the stacking, always whatever load, you have a uniform and bending. Okay, so same story goes to in second direction, in this direction. Okay, this direction, uniform and bending. Of course, we are confining the behavior and the thickness of a laminate as a kind of a thin. Okay, this is the thin. How thin is a thin? Well, compared to X and Y, let's say less than 10%, then the laminate can be called thin. So thin laminate, always the normal strain has the expressions like that. Now, shear strain, how about the shear strain? Well, it's a little bit difficult to understand, but mathematically exactly same as the normal strain. Shear strain is the constant term and linear term. What does it mean? It means that we have a variation of a shear strain, okay, variation of a shear strain. We always have a uniform shear strain and uniform shear curvatures. What is this? Well, if we look at the top, this will show deformation like this, shear deformations. Okay, this is the uniform. But how about this one? Well, this one is the twisting. Okay, twisting. So if we have a plate like that, twisting, the way we apply twisting is this way. So this will have a so can you see this plate? Can you imagine that? This is the twisted. So twisted deformation has the linear strain variation terms. While you may have some difficulties in understanding this behavior and mathematical expression, but right now, let's pay attention to mathematical definitions. But this term is relate to bending curvatures, and this is a twisting curvatures. But here, we don't have any definition of the force. Okay, this is nothing but deformation behavior. Okay, so laminate, they bonded together, they deform together. So mathematically, we do need 6 terms. 1, 2, 3, they are all constant terms. And these K1, K2, K6 are related to curvatures, okay, curvatures. And totally, we have 3 in plane, 3 curvatures to explain this each ply. See, this is the each ply deformation function of Z. So in vector terms, we simply use these equations. Epsilon bar, which is a function of Z at each ply, now has a constant terms and Z and constant terms. Of course, this one is 3 terms, and this is 3 terms, and this is 3 terms. I mean, 3 terms means 3 components. Okay? I hope you understand this. So epsilon zero, we call in-plane strain, plane-wise strain. Okay, plane-wise, and K is the curvatures. I can use a simpler explanation. Let's take a look at the beam. Okay, beam. What do we have? We have just one-dimensional structures, right? Deformation-wise, we have always 2 terms. What is that? This one can either extensions or a bending. I mean the curvatures. So any strain is a function of a Z. Z is the from here. Any function of Z now is can epsilon 0 constant term plus a Z and K. What is the K? Curvature, right? So strain through the Z. So say here always the strain is the linear and uniform and linear term. So say this one is coordinated Z, and now this is the strain, and that is a strain. This is a function of Z. And what is this? Epsilon 0, okay? And this is the slope relay is a curvature, okay? So epsilon 0 and slope curvature is a function of Z. So any strain along epsilon x, okay, x directional strain is expressed in terms of in-plane, uniform, and curvatures. Now we extend this concept to a plate. Okay, plate, and same observations in this direction. this direction and that direction, and also these deformations. Okay, so that is the kind of relation between this plate and beam. Okay, so this is the further explanation. What is the bending and twisting? So epsilon 1, you know, this is the second term. Okay, this is the second term showing linear variations. Epsilon 1 is the zk1, epsilon 6 is zk6. So zk6, this is okay, let's say this one. I mean, we had this epsilon 1, 0, okay, but we neglect that term. Let's say we only have a curvatures, and zk1, what does it mean? 1, 2, 3, 4. Just for example, 1, 2, 3, 4. This top has the extension. Here, little extension. Now the lower part, this is the compression and compressions. That is the compression means not the stress, but the deformation wise. So this is the bending curvature. Now twisting curvature. Now plus wise, this guy has the shear strain at the like that, and a little lower, still positive, and third position, you have a now starting negative strain. At the bottom, you have a quite negative strain. So bending is relatively easy to understand, plus reduced to minus, but shear, same story. I'd like to explain how this shear strain varies. They are plus is changing like that, and here, and there, and there. So at the top, you have a deformation like that, and bottom, you have a deformation like that. So if we plot them at the similar to this way, the top, you have a tension like that. This is a number 1, and number 4 is what? You have compression. So this is the deformation, right? But here is the deformations. So understanding twisting is something new, which was not observed in one-dimensional case. So understanding shear deformation is important for us to pay attention. So again, this is the A stacked. Okay, we have many plies, many plies, and stack them, and then now we twist. Okay. Pay attention, we twist like that. See the top, you can see that the shear deformation is number 1. And the bottom, shear strain wise is this way, okay? So here, and bottom. So this one, this way, you have a more extension. Do you see that? Like that? Can I? Yeah, sure. This guy, pay attention. Here is extended. Do you see that? It's a little bit extension. And this guy, you see that is a compressed. So this is the extension and this is the compressions. Now, the other way, pay attention this way. that way, the other way. You have this one now compression. At the top was a tension. Okay, so I was explaining number 1 versus number 4, and the line I draw was that line, this guy and this guy. As you can see that this one is the extension. See, shear is nothing but tension and compression in 45 degrees. So this one is the tension, and this one is the compressions. Now here, same cross line, but this one is the compression and this one is the tension. And then you can see how those strains are varying through the thickness. Each one, each ply, if you look at the inside, each one with this tension and compression are gradually changing from tension to compression and compression to a tension. That is the shear deformation, okay? That is the shear deformation. And if this cross one is a uniform, uniform means that this one and that is all same. That is the only way we apply this way, right? Then all the shear strain will remain the same, each ply. But if we twist, this shear is changing from top to bottoms. Thank you. So again, it's very interesting or very critical, important to understand this shear deformation, which varies through the thickness, okay? Now, see, don't get confused. What we have observed here is only deformation. We didn't include any load we apply. This is just deformation observation. Now, second, we like to pay attention to load, okay? Load, which is related to stresses. See, this is the strain. Sometimes we often confused by the stress and strain, but we need to be careful. These are deformation, and these are, next one is the load, okay? But conceptually, stress and strain, I mean strain and stress, and now we need to define the in-plane load and bending moments. Okay, and this one, as you can see that, a laminate, okay, laminate. And each ply, please pay attention to this line. Each ply, you have this stress, and that stress, and that stress, and that stress. Well, variation-wise, there's no rules. There's no rules control which controls stress distributions. Okay, this is very important. There is a strain. Strain is always uniform and linear deformation, but stress, there's no physical physics control the stress variation. Well, there's only one, which is the equilibrium equations. But here, we don't need to pay attention to equilibrium equation. Here, we like to emphasize that the stress can vary through the thickness. It's sigma 1 and sigma 2, and even shear, you can see that. Each ply, if you look at the ply, you know, this ply can have this much stress. And second, you have this much shear stiffness. Of course, if you have a thicker ply, a thicker laminate, we need to consider this guy. This out of a plane shear stress. Those stress can play very important, as big as this in-plane stress. But again, we are focusing on thin ply laminate. So that's why we only consider sigma in-plane stresses. Okay, so this is the observation of stresses. Now, like to define a load, in-plane load and bending moment. As mentioned, this is a sigma 1 bar, sigma 2, and sigma 6, which was indicated by this arrow, okay? And they are all function of z. So integration of sigma 1 through the z is now we define this term as the in-plane load in one direction. Well, this is the force equilibrium. Say each one, we have any stresses which we don't know, but this one, we all integration. What does it mean? Integration means we sum them up, right? We all sum them up, and which will be indicated by N1. This is the load, and this is the stresses. Stresses, we multiply through the thickness, and we got the load. So this is the unit-wise, this is the Pascal, so Newton per meter square, times meters. So this will be Newton times meter, I'm sorry, divide. But the reason is that if we consider this width, okay, this width or length, then we multiply length, then we will get total load N. But this in-plane load is defined as a Newton per length. Okay, Newton per length. So we integrate only through the thickness. Okay. Stress times thickness. And N2 is the same. N2 goes this way, and integrations, and that will be the in-plane load. And N6 is the same. Stresses goes like that. N6 integrate. So these three equations give us a definition of in-plane load, N1 to 6. And in short, we can say N is the vector form. N indicate N1 to 6, and sigma is these three terms. So these are 3 term and 3 term, and we can say this is the, this way. Now, moment. How about the moment? Well, again, we start from this moment, the stress distributions. And to define the moment, what do we need to do? We multiply Z, right? Thickness Z, and then integrate, which will give us the moment 1 and sigma 1 to, moment 2 and sigma 6, Z and moment 6. Okay, so this is the moment, and these all three equations, moment and sigma. So this is the, as you can see, these terms and these terms. Okay. Now, this one, final step in derivation of ply stiffness. We are combining this definition and these definitions. Okay, we're combining them. How do we do that? Well, we already have this relation, O-axis. O-axis stress-strain relation was stiffness. we already have this term in each ply in Excel, right? We have all Q bar in each ply in Excel, each column. Now, using this equation and defining this, what is this? This is the definition of in-plane strain, and this is the sigma bar. Now, sigma bar has a relation with epsilon bar. So we put this equation into here, okay? And then this one, sigma bar, has the relations like that. See, epsilon bar goes like that. And so this stress is like that. So epsilon bar has the strain at each ply, but each ply strain has is a given constant and linear terms. Okay, so sigma bar, sorry, this goes that, and this goes into here. And sigma bar, now you have a Q bar, stiffness through the thickness. But this epsilon 0 is what? Is a function of z or constant? They are all constant. So it has nothing to do with the integration. So this is the a constant out of integrations, right? And second term, Q bar and z, okay, z, well, z of course cannot, get out of integration. But k, what is the k? Is it constant? Yes, it's a constant. So integration, out of integration. But here, n is not just one component. N means that what? N1, N2, and N6, right? Well, sigma is not a one component, which has also these three components. Sorry, this has to be 6, and 6, and 6, and 6, 6, 6, 6, 6. Okay, so well, all three components or 3 by 3 component, but mathematically we just use this one equations, and the point here is the epsilon 0 is a vector, it's still out of integration, and k is a vector, is still out of integration. Now, what is this term? Dimension-wise, what's the size of this Q integration? It's a 3 by 3. Why? See, Q bar is this guy, and put it into this one here. So I like to repeat here. Q bar, dz, what does it mean? In component-wise, integration Q11 dz, integration Q12 dz, integration Q16 dz. Okay, integration Q22 and so on. Okay, this is the mathematical expressions of a Q bar dz. Okay, we have a 3 by 3 and we do need to integrate each terms. But understanding wise is much easier to use this Q as a matrix. Okay, now definition of a moment. Okay, definition of a moment. Moment is a sigma times z. Sigma times z, okay, z, and sigma is here, put it there. So we have also constant terms and linear terms. But here, please pay attention, we have a z multiply here. So the z, we do have a z, and we had a z here, now we have a z square. right? So this one, 3 by 3, you can call A matrix. And this one, we do have a Z. So when you integrate, if we have a Z here, we need to have a Z here, Z here, Z, all the terms. So this is a B. We just call this is a B, which is also 3 by 3 matrix. And this is D, D. Now we have a Z square. And here B, see this B and this B, they are same. Right? So it's a symmetric matrix. Okay, so this is the final. This is the in-plane load and bending moment, and in-plane strain and curvature. This ABD, so famous matrix, ABD matrix, which represent the stiffness of a laminate. How do we calculate the A? Well, A, we integrate all the Q through the thickness, and so on. Well, I just entered ABD matrix. You can see that how many results you get. This is a basic mechanics of a laminate composite plate. You can see that ABD, all you can find from all internet, which means that we commonly use the symbol A is B and D. As you can see, this is the A matrix, B matrix, and D. And as you can see, this is the 3 in-plane strain and 3 curvatures. Okay, so this term not shown here, but on the left, this should be NX. Well, here we use the N1, N2, N6, but depending on the books, they use the XY and NY, but it's the same. So 3 in plane, 3 moments, and this is the well, good to know, have these terms, how to see how others are using. Exactly same. Now, instead of this 3 by 3, we used this one. Now, in terms of a component, we have N 3 terms, M 3 terms, and this ABD is a totally what? 6 by 6 matrix. Okay, 6 by 6. So they are so famous matrix called ABD matrix. Okay, ABD matrix. Now, how do we calculate that? Well, mathematically, here, this is the A, and this is a B, and this is a D matrix. Okay, so let's say, how do we practically calculate from a laminate? This is the equations. Okay, this is the equations. So this is how we calculate. I hope we can complete this programming today. So this is the A matrix, okay, from definition. Please remember this is a 3 by 3 and Q is a 3 by 3. And integration means from bottom to top. Total, we have ADs, and total, we have H thickness, and this is a middle, and from here is a half thickness, and from bottom is a minus half thickness. And this, mathematically, how do we calculate that one? Well, each ply, okay, each ply, we have a different Q. So what we need to do is that, for example, let's say we pay attention to just one ply, okay, one ply. This is the integration of a one ply, and then we can sum this integration from all plies. So this one ply, as you can see, Z I to Zi plus 1. So which means that this from here to there, this is a Z. I like to use K, okay, ZK to a ZK1. It's a little bit. Okay, so this one from the here, the ZK and top, we have a ZK1. Okay, so this is the integration for each ply, and then we sum them up. So how do we calculate this one? Each ply. Well, fortunately, this is the constant, right? Constant. So constant and integrate from here to there. So we just ZK plus 1 minus ZK. Right? How about the B matrix? Okay, B matrix. Well, exactly same procedures, but only difference is that this Z integrate each ply, and each ply, now this one is a constant out of integration, and Z is still Z there, and all we need to do is the integration Z from this each ply, okay, this ply. So this is the one, each ply. Now, ZK plus 1, instead of that, we have a scale because we had to integrate the Z. Now we have a D matrix. D matrix, now we have a Z scale, and exactly the same procedures except these Z terms. Z scale, we integrate now 1/3, and so this one is the each ply K, and this one is the each ply. We have a K plus 1 and K. Okay, this is the a kind of algorithm that we can calculate ABD matrix from each ply stiffness. So in doing so, what do we need to define? Okay, what we need to do is that we need to have a ZK, right? ZK. So ZK is this guy. ZK is the coordinate of this one. This is a Z1 and Z2, Z3, and so on. So let's define the ZK. Then others, next step is just the integration and then sum them up. So ZK, there is any terms? ZK. Well, to calculate the ZK, total thickness will be these terms. Total thickness, we need to
calculate the total thickness. Now, we need to have, we didn't have a ply thickness, right? We didn't have a ply thickness. Now we define a thickness. Thickness means each ply thickness. So you can say, oh, I like to have a 1 millimeters. I mean, this is a meters, but millimeters. Oh, I like to have a 1 millimeters and any plies as you like. Okay, this is a thickness. So let's say we have a, this is the a variable called thickness. Now, how do we define a z? See, the z, I will call zk. Zk is the starting from bottom, z1, z2, z3, and so on, and up to top, right? So to calculate the zk, we need to calculate a total thickness. So this is a total thickness. We sum them up. Total thickness. So I will call this guy a total, I would say H, okay? So this is the variable total H. Now, Zk is what? Starting from a total H, divide by 2, and minus. See, at the bottom, right? And then next one is what? This guy plus this thickness and so on. So as you can see that this is a ply, each ply thickness. Now this is a z coordinate. Oops. Why? Okay, that is right. And this is the, see, one thing we need to be careful is that, see, we have many plies, and this one is the Z1, 2, and so on, and this is a AZ. If we have a number of plies, N, so this will be N plus 1, right? Top, and this one is a Zn, because this one is the coordinate of each ply position, and this is a number of plies. So that's why it's starting from minus, and here is the 1 ply thinner. So we like to define a Z K1. K1 means that 1 ply up. So ZK1 is this plus what? Thickness. And I like to use this one as same as that one, and this one same as that, and copy and here. See, it's nothing, special. So from the bottom and 1 ply up, and same 1 ply up, and same, because this one, this one, and that is the same, right? And this one is the same ply. So this one
at the first ply, you have a z plus 1, but at the second ply, it will be a z1. Okay, so let's give a name, define the name. Okay, so we have a variable called zk and zk1. Now, how do we calculate A matrix? First, we need to follow these terms. Okay, let's follow this one. See, this one, we sum them up. So this only one term for each ply. This term will be called A11. So this one. So we have how many terms? We have A22, we have a same here. So we have a A11, A22, and so on. We will sum them up. So here equal Q11, okay? Please here, here times what? ZK1 minus ZK. That is a A11. And then summation. Summation means that we all the sum, and then we need to, this one, we define, and this will be the sum. Sum of the A11. So basically, this one is the A11. Okay, I like to call this is the each component, okay? Not the A11. So I will just use just different symbols, A components. Component means that this term, okay? And we need to sum them up. So this one, we will have a, okay, I will redefine this one as the, like that, and this one, now we do this. Oops. Okay, and then here. Okay, this one will be ABD matrix. Okay, so now next move to A22. A22. A22 is the, we simply change this one, I mean, instead of Q, we have a 22. And so here, instead of a 1, 2, we have a Q12. Here, instead of a 6, 6, and 1, 6, and 2, 6. Okay, so just copy and paste, and here we just integrate to 2 and 1, 2 and 6, 6 and 1, 6, and 2, 6. Okay, so this is the A matrix. Little bit, you know, we have to go through some step, but mathematically, a simple, this all the procedure is this one. Again, if you like to double check, you can see that all the equations, Q11, this is the same as that one, right? Q11, Q22, and this term again is not the one term, it's a 3 by 3. You can see that 3 by 3, all the same. You can double check the equations and you sum them up, and this is the final ABD matrix. Okay, let's move to a B matrix and D matrix. And instead of here, what do we need to do? See, we have now here, we extend it to square. Okay, this is the B matrix and square. So all you need to do is that here you have a square, and divide by 2. And let's do that. And let's do that. And here. And here. Okay, so copy and paste. And this guy, now we change it to A to B. Okay, and then change the name as a B. And now here, oops, we have to change this one too. Oops. A to B. And that is the definition of a B matrix. Okay. Okay. And this one, now D matrix. We like to have a D matrix and 3, 3, and 3. Well, we could define as a 1 value, but like to use the same equations as the definitions, and we just change this one. But again, you can define this one as a 1 value. You don't have to repeat these terms. Okay, so now from here to there, you change from A to D and change the name up to here as the D matrix. And here you have a D, and now you have a definitions of this one. Okay, done. So this is the A matrix and B matrix and D matrix. We like to use this term as a matrix form. So what do you need to do? Well, we can use a 3 by 3 matrix. So this one, A11, here, A12, A16, and here A22,
and here A 1 2 6, and here A 6 6, and here is what B 1 1, here B 1 2, here B 1 6. And then this is the what? B 2 2 and B 2 6, and here B 6 6. Okay, here is a symmetric. This one same as that. Symmetric here same as that, and here same as that. And you can change just here, and let's replace A to D. Okay, and now symmetric. You can say this is this, and that, and that, and that, and that. This one, that, that. Okay, that, that, this, that, that, that. This one, that. Okay, so this one, what is it called? Let's call ABD matrix. Finally, so this is the ABD matrix. Again, givens are all these blue numbers. Okay, sorry, this is the not the. See, this one is the blue as an input. And this one, you can see that this is the ABD matrix here. Like to use a red one. So flow-wise, I can delete this one and this one. Flow-wise, say starting from here, you can always follow this cell goes to there, goes to there, goes to there, and goes to there. Okay, you need to be sum them up, right? And then all goes to here. Okay, so each ply starting from material property and thickness and angle and ply stiffness on axis. This is the UD stiffness, and this is the what? This is the UD on axis stiffness, you can call. This is the, you can say off axis and invariant, well, same as that one. And this one is the A matrix, A stiffness, it's okay. And this one is the B and D, and this is the B, and this is the D. Okay, I wonder we can, let's try. Can we,
How do you have it this way? Okay, so this one, now you can format anytime. Line numbers, and these are again the information you need to specify. Okay, let's format the later, but anyhow, these are given, and finally we can have a ABD matrix, right? Why so important, this ABD matrix? Well, we will do next week, but let's say, okay, let's say this is the if you go to here, this is the ABD matrix. Now, ABD matrix, we apply the load, N and M. How do we calculate the deformation? Well, deformation epsilon and K. All you need to do is you invert this matrix and multiply this, and you get this, right? So how do we inverse? 1, 2, 3, 1, 2, 3. So this is the a matrix, and equal matrix inverse and AB, what we call ABD matrix, right? So that's it. This is the inverse matrix of this guy. And now we need to do is that we multiply what? N, let's call load, okay? Load means that this is the N1, N2, any values, moment 1, moment 2, and moment any value. Now you can get this strain and curvature is by M multiply this guy and comma and this guy. This guy we call load, right? Okay, so you can immediately get the strain, 3 strain and 3 curvatures. Very straightforward. As long as you have an ABD matrix, you get this one. So it's important to have this value. So I like to move this up. Okay, let's close our class today. So here, this one is the our define this. This is the what? N1 and N2, N6, and moment 1 and moment 2 and moment 6. That is the load we are applying, okay? So input, I will change it to a color, blue. Okay, this is the input. You specify how much load you apply each directions. And then the output will be say E1 0 and E2, I mean in-plane strain, and in-plane strain 6, and this is what? Curvature 1, curvature 2, and curvature 6. Okay, so this one again equal M mult M inverse of what? ABD matrix times this guy. Let's call a load. Okay. Okay. So this one I will change the name as a load. Okay, so this one as the output as in red color. So this is the input, and this is the input, and this is the output. Okay, so as you can see that this goes to this, and so, and comes to here, final value, and starting from this and that, you got this. Okay, so this is the program you need to go this week. Okay. Any questions? Very easy, huh? Okay, so once you have this much programming, you can play with very different. You can do many things. Say this is what let's say. I like to have all UD. All you need to do is just enter all 0. Then this is just a UD laminate. Or I like to have a cosi as a 0 plus 45 minus 45, 90, 90, and minus 45 and plus 45.
You can
0 up. How to delete them? Well, thickness is 0. Thickness 0 means we don't have any ply. So this is how we define the 8 plies out of this. But there could be, so as you can see, this becomes a 0 when you sum them up. When you sum them up, it's automatically 0, right? So whenever you want to neglect certain ply, you just enter the 0 for the thickness. And this is the how you get the strain. Look at the strain values. Say this is the all what? All we just apply tension. What do you get? Epsilon 1 is extension, and epsilon 2, what do you get? Little bit of a contraction. You know the definition of a minus, there is a minus. If you look at this ratio is divided by this. What is this? This is a Poisson's ratio of a laminate. The Poisson's ratio, you always have a minus. Okay? So, this is a quasi-isotropy laminate. This is the A Poisson's ratio of this laminate. And here, what is that? Almost a 0, right? So minus 26. As you can see, these are all 0. And what if I apply this and that same load? Of course, there will be same strain in 1 and 2 direction, and others are all 0. What if I apply only shear? You can see only shear. What if I apply only bending moment? You will see curvature. They are all 0. And do you see this one, K2 is a non-zero? And you can see if we have a ratio between these two curvature, we have also a 0.3. What is this curvature, two curvature when we apply the bending moment? Okay, this is a laminate. We apply this moment. Okay, I cannot demonstrate precisely, but whenever we have this moment, which is the M1 equal 1, right? This is the only apply, the load we apply, but curvature-wise, we have a two curvature, which means that this way, we have a curvature, K2 minus. What is the minus? This way, but this one is this way, oh sorry, this way, but this way is this way. I like to draw. So if we have a plate like that, and we have a bending moment, always we have a bending and anti-bending. See, this is the moment we apply, but this is the curvature one, and this is the reverse curvature in the other directions. Okay, so please, this is this way, and that is the other way. That's the meaning of the minus curvature. This is a plus curvature, minus curvature this way, but this way is this curvature. This is called anti-curvature. It happens to any material, any structure, even for the isotropic materials. So that is the very important observation. And you can play with many different angles, many different loads, and so on. Okay, so this is the, now we don't need to have this one. This one is not so important right now, but this input and output is important. Okay, any questions? Now it's precise the 350. Okay. While you have a lot of things to do this week, okay, you need to went through this programming. I'm gonna delete my Excel. You have to do it yourself. Okay. Okay. Don't forget, delete. Don't upload it. You have to do it, and then using your tools, I will assign homework, numerical evaluation. Say some angles, laminate sequence, what will be the strain, and how much load you apply, and so on. Okay, so we are almost finished all the theory. Any questions? Well, I'm a little sorry. I move very fast, but I like to cover this much. Okay, thank you so much, and see you next week.
저희가 그럼 지금 교실에서 학회 가는데 월화 수를 줍니다. 그래서 코드 학회. 코드 학회.
코드 학회가 뭐야?
페이저널
어느 그래?
저희 연구실에서 총 2명이 가시는데
그래? 뭐 가야지.
예, 그러면 저희 빠진 거에 대해서는
그게 중요한 게 아니라 이 녹화를 하니까. 잠깐만.